In this module, you will learn how to make inferences about the mean of a single population when sample is large and when it is small, keeping in mind the form of the population distribution. You will also learn how to make inferences about the proportion of successes for a single population. Although the sample statistic used is the same for estimation and testing, but the value of the parameter used in the two cases will differ. Next, you will learn how to make inferences about population variances in the single population, how to test for the form of the population, how to test for independence of two random variables which may or may not have numerical values. To begin with, inferences can be about a single population parameter or about parameters of more than one population. A point estimate or interval estimate can be made of unknown parameters by observing sample data. In other cases, we may be presented with a claim about the parameter value, and we can use sample data to investigate the authenticity of the claim value. Nature of inferences to be made depends on the type of problem. The procedure of reaching conclusion depends on the type of population, sample size, the number of parameters, and other unknowns. The test statistic used is the same for both types of inferences. In some instances, we may want to check if the population has a particular form. First, we will discuss inferences about the single population mean. A random sample of n observations is drawn from the population. The sample mean is an unbiased estimator of the population mean. The point estimate of population mean mu is obtained by substituting values of sample observations in the formula of sample mean so that mu hat equals x bar equals sum of xi's divided by n. The interval estimate is centered at x bar. The limits of the confidence interval and tests of a hypothesis about mu depend on assumptions made about the population and the sample size. Now we will discuss distribution of sample means when population is normal or sample is large. If population is normally distributed with a known variance, then the distribution of sample means is also normal with mean mu and standard error sigma by root n for all sample sizes. The standardized variable z equals x bar minus mu divided by sigma upon root n, and it is distributed normally with mean 0 and variance 1. If population is not normal with known sigma but sample size is large, so the sample is at least 30, then x bar has approximately a normal distribution. If population variance is unknown and estimated by sample variance, where sigma hat squared is equal to s squared, which is equal to the sum of the squares of xi minus x bar divided by n minus 1, but sample size n is at least 40, then also x bar is approximately normally distributed. In both these last sample cases, the standardized variable z is equal to x bar minus mu divided by s upon root n, and it has an approximately standard normal distribution. The denominator of the z statistic is the standard error of x bar, denoted by SE subscript x bar. The 100 times 1 minus alpha percent confidence interval for mu is x bar plus minus z alpha by 2 standard error of x bar, which is written as the lower limit x bar minus z alpha by 2 standard error x bar, and the upper limit x bar plus z alpha by 2 standard error x bar. The maximum error of estimation, which is half the interval width, can be controlled at a specified level by adjusting the sample size. Now we will discuss the testing for value of population mean. When testing for the value of population mean, the Z statistic is calculated from sample data under the assumption that the claimed or null value mu equal to mu naught is true. That is, the calculated value of Z is equal to x bar minus mu naught upon the standard error of x bar. This is then compared with the critical values of Z. The Z critical values will depend on the level of significance alpha selected for the test and on the alternative hypothesis, that is, whether it is a lower tailed or upper tailed or two-tailed test. The table presents schematically the three different types of tests along with rejection regions for some commonly used critical values of the test statistic. We have the null hypothesis H naught mu equal to mu naught, where mu naught is the initial or claimed or null value of mu. As can be seen in the table below, for the alpha levels 1%, 5%, and 10%, and the upper tail test, we have the Z critical values 2.33, 1.645, and 1.28 respectively, which is defining the rejection regions as any Z value which is greater than equal to any of these critical values for the respective alpha levels. Similarly, for the lower tail test, the critical values of Z will be having a negative sign. For the two-tail test, the Z critical values are plus minus 2.58 for the 1% level, plus minus 1.96 for the 5% level, and plus minus 1.645 for the 10% level. Once we know what the critical values are, we can define the rejection regions. For the upper tail test, it will be all Z values that are at least equal to the critical value or more than that. For the lower tail test, the rejection region lies to the left of the Z critical value, and for the two tail test, the rejection region is divided at the two tails of the Z distribution, half to the left of minus Z alpha by 2 and the remaining half to the right of plus Z alpha by 2. Other levels of significance can also be used depending on the desired maximum probability of type 1 error. The critical values for defining the critical region can be found in the table for the Z distribution. The p-value method can also be used where other levels of significance can also be used depending on the desired maximum probability of type 1 error. The critical values for defining the critical region can be found in the table for the Z distribution. The p-value method can also be used where p-value is the upper tail area to the right of the calculated value of Z in the upper tail test, the lower tail area to the left of minus ZC for the lower tail test, and sum of the two tail areas for the two tail test. Decision rule is do not reject the null hypothesis if p-value is more than the level of significance of the test and reject otherwise. Note that interval estimation and tests of hypothesis are two sides of the same coin. The values of the test statistic that fall in the confidence interval at confidence level 1 minus alpha and the values of the test statistic from the same distribution that lie in the critical region at significance level alpha are disjoint sets. Therefore, a test statistic that does not lie in the confidence interval must naturally lead to the rejection of the null hypothesis. Next, we will discuss small sample inferences for mean. When the sample is small and population variance is unknown, then the Z test is no longer applicable. If the population is normally distributed and population variance is estimated by sample variance, then the standardized variable will have a t distribution. The t distribution is symmetric and centered at 0 but more spread out than the z distribution. The greater variability in the distribution arises because the denominator of t, which is equal to x bar minus mu divided by s upon root n, varies with the value of sample standard deviation from one sample to another. The t distribution has a single parameter, its degrees of freedom. The distribution is a family of curves, each identified by its degrees of freedom nu. Now we will talk about degrees of freedom and confidence interval. The degrees of freedom are associated with the sample variance. Since S squared has n minus 1 degrees of freedom, therefore the t curve has n minus 1 degrees of freedom. Each row of the t-table represents the distribution for a specified degrees of freedom and gives t-critical values for some commonly used alpha levels for the upper tail. Since the distribution is symmetric, the lower tail critical values are the same with a minus sign. Note that the t distribution approaches the z distribution as n increases. This is the reason we use the z critical values in inferences about the mean when sample size is large, even when population variance has to be estimated. Using the table of critical values for the t distribution, we can obtain the confidence interval for population mean and test for the value of the mean. The 1 minus alpha level two-sided confidence interval for mu has a lower limit x bar minus t alpha by 2 n minus 1 times s upon root n, and the upper limit is x bar plus t alpha by 2 n minus 1 times s upon root n, where plus minus t alpha by 2 n minus 1 are the critical values. Here alpha by 2 is the area under the curve in each tail of the distribution. The upper bound and lower bound confidence intervals can be obtained by using the critical value minus t alpha n minus 1 for the lower bound confidence interval or plus t alpha n minus 1 for the upper bound confidence interval. Then area in the tail is alpha. Thus, the 1 minus alpha percent upper bound confidence interval is minus infinity at the lower level, and the upper limit is x bar plus t alpha n minus 1 times s upon root n. Similarly, the 1 minus alpha percent lower bound confidence interval is x bar minus t alpha n minus 1 s upon root n as the lower limit and infinity as the upper limit. Width of the interval depends on t critical values, which again are dependent on the sample size. Also, the width depends on the sample standard deviation and the sample size. Therefore, it is not possible to obtain required sample size n for desired width, as n has to be decided before collecting the sample, but s is known only after sample is observed. When testing the hypothesis H naught mu equal to mu naught versus H1 mu greater than mu naught or H1 mu less than mu naught or H1 mu not equal to mu naught, the test statistic is T, which equals x bar minus mu naught divided by S upon root n. A random sample of n observations selected from the normal population yields a sample mean x bar, and the calculated value of the test statistic is then Tc equal to x bar minus mu naught upon S upon root n, under the assumption that the null hypothesis is true until sample evidence strongly favors the alternative. The rejection regions for the upper tailed, lower tailed, and two-tailed tests are respectively R for all calculated values greater than equal to T alpha nu, then R for all calculated values of T which are less than equal to minus T alpha nu, and R for all calculated values of T which are less than equal to minus T alpha by 2 nu, or Tc greater than equal to T alpha by 2 nu for the alpha level test. The only difference between the z-test and the t-test is that the critical value for given alpha remains the same for all sample sizes in the z-test, but varies in case of the t-test for different sample sizes, since the degrees of freedom nu is equal to n minus 1. The t-test is quite robust. Even when the population is not normal, if sample is not too small, the test can be used as long as the population does not diverge too much from a normal distribution. Let us clarify more with the help of an example. The shelf life of milk packaged by a manufacturer is normally distributed with a mean of 10 days. The manufacturer claims that introduction of a new technique in the packaging process can increase the shelf life of milk. A sample of 16 milk packets produced by the new process is tested, and the mean shelf life of the sample is found to be 11 days with a standard deviation of 2 days. Is the manufacturer's claim justified at the 5% level of significance? This can be solved as follows. The population is normally distributed, but variance is unknown and the sample is small. So we use a t-test. The null value mu naught is equal to 10, sample size n is equal to 16, sample mean x bar equals 11, and the sample standard deviation s is equal to 2. The null hypothesis is mu equal to 10 versus the alternative h1 mu greater than 10. The calculated value of the test statistic Tc is equal to 11 minus 10 divided by 2 upon root of 16, which is equal to 2, where degrees of freedom is 15. Now, the critical value is T 0.0515, which is equal to 1.753. The critical value 1.753 is less than the calculated value 2. Therefore, the null hypothesis is rejected at the 5% level of significance, thus justifying the manufacturer's claim. The p-value approach to testing can also be used. For this, we would require a separate table that gives the t-curve tail areas. This table too gives tail areas for the upper tail of the distribution only. Since it is a symmetric distribution, the lower tail area for minus T alpha nu is the same as that for T alpha nu. For the two-tail test, you would have to take twice the value given in the table. Once the p-value is found, then we reject H naught if p-value is less than equal to alpha. If p-value is greater than alpha, we cannot reject H naught at alpha level of significance, and the null hypothesis remains plausible. Another example could be, at what alpha level would the conclusion in the above example be reversed? This can be solved as, for Tc equal to 2 and nu equal to 15, the p-value obtained from the table for T-curve areas is 0.032. We would fail to reject the null hypothesis if alpha is less than or equal to 0.032, that is at significance level 3.2% or less. Next, we will talk about inferences about single population proportion. The sample proportion x upon n is an unbiased point estimator of population proportion P, where x is the number of successes in n independent trials that make up the sample. Now, x is distributed binomially with parameters n and p, where expected value of x is np and standard deviation of x is square root of np times 1 minus p. This gives us p hat equal to x upon n and sigma p hat equal to the square root of p times 1 minus p upon n, which is equal to the root of pq upon n, where q is equal to 1 minus p. If both np is greater than equal to 10 and nq is greater than equal to 10, then X has approximately a normal distribution provided the sample is small relative to the population, where a sample is considered small if it is no more than 5% of the population. If X has approximately a normal distribution, then p hat, which is equal to X upon n, is also approximately normally distributed. Standardizing p hat, we get the 1 minus alpha percent confidence interval for p as follows. Probability that p hat minus p upon square root of p times 1 minus p upon n lies between minus z alpha by 2 and z alpha by 2 is approximately 1 minus alpha. The confidence limits are obtained by replacing the less than sign with the equal sign. This gives us p hat minus p equal to plus minus z alpha by 2 times square root of p times 1 minus p upon n. Squaring both sides, p hat squared minus 2 times p hat p plus p squared is equal to z alpha by 2 square times p multiplied by 1 minus p upon n. Multiplying through by n and rearranging the terms, we get n p hat squared minus 2n times p hat p plus np squared minus z squared alpha by 2 p plus z squared alpha by 2 p squared equal to 0. Collecting the terms, p squared times bracket open n plus z squared alpha by 2 bracket close minus p times bracket open 2n p hat plus z squared alpha by 2 bracket close plus n times p hat squared equals to 0. Let A equal to bracket open n plus z squared alpha by 2 bracket close, B equal to minus bracket open 2n p hat plus z squared alpha by 2 bracket close and C equal to n p hat squared, so that we have the quadratic equation ap squared plus bp plus c equal to 0. Solving for p equal to minus b plus minus square root of b squared minus 4ac upon 2a, where we substitute the values of a, b and c in the formula to get dividing the numerator and denominator by 2n and substituting 1 minus p hat equals q hat, we obtain the formula for p equal to p hat plus z squared alpha by 2 upon 2n plus minus z alpha by 2 times square root of p hat q hat upon n plus z squared alpha by 2 upon 4n squared, the whole thing divided by 1 plus z squared alpha by 2 upon n. If sample size is large, so that np hat is greater than equal to 10 and q hat is greater than equal to 10, then z squared alpha by 2 upon 2n, z squared alpha by 2 upon 4n squared in the numerator and z squared alpha by 2 upon n in the denominator will be very close to 0, so that the confidence limits of p are p hat plus minus z alpha by 2 times square root of p hat q hat upon n for the 1 minus alpha level of confidence. The two-sided confidence interval for large samples is therefore p hat minus z alpha by 2 times square root of p hat q hat upon n as a lower limit and p hat plus z alpha by 2 square root of p hat q hat upon n for the upper limit. And the probability that the population proportion will lie between this lower limit and the upper limit is approximately 1 minus alpha. Width of the interval is 2 times z alpha by 2 square root of p hat q hat upon n. However, the traditional formula for confidence interval p hat plus minus z alpha by 2 square root of p hat q hat upon n may result in a probability that is different from the specified probability 1 minus alpha for the selected z alpha by 2 even for a reasonably large n, particularly when the probabilities of success and failure are quite different. That is, they are not close to 0.5. But the score interval p equal to p hat plus z squared alpha by 2n plus minus z alpha by 2 square root of p hat q hat upon n plus z squared alpha by 2 upon 4n squared whole thing divided by 1 plus z squared alpha by 2 by n does not suffer from this deficiency and can be used for all sample sizes and all values of p. If we wish to find the sample size that results in a desired level of confidence or reliability, that is 1 minus alpha, and specified width or precision W, we obtain required sample size as n must be greater than or equal to 4 z squared alpha by 2 p hat q hat divided by W squared. This, however, requires p hat, which becomes known only after the sample has been selected. But n has to be decided before drawing the sample. Thus, required sample size is not easily obtained without information of the likely values of p hat and q hat. One approach is to consider p hat equal to q hat equal to half for the purpose of calculating sample size. The width is maximum if the probabilities of success and failure are equal. Then n is greater than or equal to z squared alpha by 2 upon w squared. The one-sided confidence intervals are, however, not unbounded. Since p lies between 0 and 1, the lower and upper confidence intervals using the traditional formula are p hat minus z alpha by 2 sp hat comma 1 and 0 comma p hat plus z alpha by 2 s p hat respectively. This can be better explained with the help of an example. Headhunter companies are responsible for the placement of many of the CEOs of a country's companies. A business magazine has reported that 1 out of every 4 CEOs is an outsider, that is, an executive with less than 5 years at the company he runs. If in a sample of 350 companies, 77 have outsider CEOs, would a 99% confidence interval support the magazine report? Explain. This can be solved as follows. The reported proportion is p equal to 0.25. The sample size is 350 with p hat equal to 77 upon 350 which is equal to 0.22. Since sample is large, the 99% confidence interval for p is 0.22 plus minus 2.58 times square root of 0.22 multiplied by 0.78 divided by 350, which is equal to 0.22 plus minus 0.057. So the lower limit is 0.167 and the upper limit is 0.277. Since 0.25 lies in the interval 0.163 to 0.277, the 99% confidence interval supports the magazine report. Next, we will discuss test for proportion. When testing the hypothesis H naught P equal to P naught versus the alternative P greater than P naught or P less than P naught or P not equal to P naught, we need to use different test statistics for large samples and small samples. If sample is large, where NP greater than equal to 10 and NQ greater than equal to 10, but small relative to the population, sample is not more than 5% of the population size, the distribution of sample proportion p hat can be approximated by the normal distribution. The test statistic is calculated under the assumption that the true proportion is P naught. So the standard error is square root of P naught Q naught by N, where Q naught is 1 minus P naught. P hat is a sample proportion and the test statistic is Z equal to P hat minus P naught divided by the square root of P naught Q naught by N. The decision rule using the calculated value ZC is the same as in table 1 for the upper, lower and two-tailed tests. Note that the standard error of p hat differs from the one used in interval estimation. In confidence intervals, we do not have a given none value and standard error of p hat is equal to square root of p hat q hat upon n. When testing the null hypothesis, standard error of p hat is equal to square root of p naught q naught upon n, as we assume that the expected value p hat equal to p naught until the null is rejected. Illustrating it with an example as follows. A national news service is running a poll to determine if the majority of the population of Delhi is in favor of removing subsidy. Out of a random sample of 100 people, 56 were found to be in favor of removal of the subsidy. Is this strong enough evidence at the 5% level of significance that the majority of the population of Delhi favors the policy change? This can be solved as, now n is given to be 100, x is equal to 56. This implies p hat equal to 0.56 and q hat equal to 0.44. The null hypothesis is p equal to 0.5 to be tested versus the alternative that p is greater than 0.5. Since sample is large, we use the z-test. The calculated value of z, 0.56 minus 0.50 upon the square root of 0.5 squared upon 100 works out to 1.2. For the 5% level of significance, the critical value of z is equal to 1.645, which is more than 1.2. We do not reject the null hypothesis and conclude that majority are not in favor of policy change. If the sample is small, then we need to use the binomial distribution, as a normal approximation to the binomial distribution is no longer valid. Another example could be, a builder claims that LED lamps are installed in 70% of all homes being constructed today in its new project. Would you agree with this claim if a random survey of new homes found that 8 out of 15 had LED lamps installed? Use a p-value to test at the 10% level of significance. Solving it as follows. This is a test for proportion using the binomial distribution, as the population size is unknown and we cannot assume a normal approximation to the binomial distribution. Test statistic is a binomial variable x with p equal to 0.7 and n equal to 15. We test the null hypothesis p equal to 0.7 versus the alternative p not equal to 0.7. Since x is equal to 8, n times p naught is equal to 15 times 0.7, which is 10.5. From the table of cumulative binomial probabilities, p value is equal to 2 times the probability that x less than equal to 8 when p equal to 0.7, which is equal to 0.2622, that is greater than 0.10. We do not reject the null hypothesis and conclude that the sample evidence is not significantly different from the builder's claim. Next, we will talk about inferences about the single population variance. The unbiased point estimate of population variance when n and x bar are the sample size and the sample mean respectively is the sample variance s squared, which is equal to summation of the square of xi minus x bar divided by n minus 1. If a random sample of size n is selected from a normal population, then the random variable n minus 1 times s squared upon sigma squared, which is equal to sigma xi minus x bar squared upon sigma squared, has a chi-square distribution with n minus 1 degrees of freedom. The chi-square distribution is positively skewed continuous probability distribution with a single parameter nu. The density function is f of x given nu. It is greater than 0 for x greater than 0 and 0 otherwise. Thus, chi-squared is greater than equal to 0 always. As nu increases, the distribution becomes more symmetric. The chi-squared table gives critical values of chi-squared alpha nu such that the area in the upper tail of the distribution with nu degrees of freedom is alpha. As the value of chi-squared alpha nu increases, we move further away from the origin, and as a result, the upper tail area alpha decreases as shown in the graph. Since the random variable n minus 1 times s squared upon sigma squared is a function of sigma squared and its probability distribution chi squared n minus 1 does not depend on sigma squared, it can be used to construct the confidence interval for population variance sigma squared and standard deviation sigma, provided the population is normally distributed. Since area under the chi-squared curve to the left of chi-squared 1 minus alpha by 2 is equal to the area to the right of chi-squared alpha by 2v and each area is equal to alpha by 2, we have the probability that n minus 1 times s squared upon sigma squared lies between chi-squared 1 minus alpha by 2 nu and chi-squared alpha by 2 nu equal to 1 minus alpha. Rearranging the terms, we get the probability that sigma squared lies between the lower limit n minus 1 times s squared upon chi squared alpha by 2 n minus 1 and the upper limit n minus 1 s squared upon chi squared 1 minus alpha by 2 n minus 1 is equal to 1 minus alpha. Therefore, the 100 times 1 minus alpha percent confidence interval for sigma squared is the lower limit n minus 1 s squared upon chi squared alpha by 2 n minus 1 and the upper limit n minus 1 s squared upon chi squared 1 minus alpha by 2 n minus 1. The 1 minus alpha confidence interval for sigma is obtained by taking the square root of the upper and lower limits of the 100 times 1 minus alpha percent confidence interval for sigma squared, so that the two limits are respectively square root of n minus 1 s squared upon chi squared alpha by 2 n minus 1 and square root of n minus 1 s squared upon chi squared 1 minus alpha by 2 n minus 1. Note that the confidence interval for sigma can be found only after obtaining the confidence interval for sigma squared, since the chi-square distribution is only applicable for the variance. Also note that it is difficult to find the confidence interval for variance if the population is not normal even when the sample is large. Next, we discuss the test for variance. The test for variance also relies on the chi-square distribution. If the null value is sigma squared naught, the null hypothesis is H naught, that sigma squared equal to sigma squared naught. The alternative hypotheses are sigma squared greater than sigma squared naught, or sigma squared less than sigma squared naught, or sigma squared not equal to sigma squared naught. For the alpha level test, we have to select the critical values of the chi-squared nu statistic for the appropriate degrees of freedom nu equal to n minus 1, where the sample is of size n. The test statistic is chi squared n minus 1 equal to n minus 1 times s squared upon sigma squared naught with degrees of freedom equal to n minus 1. For the alternative hypothesis H1 that sigma squared is greater than sigma squared naught, the rejection region is R for all values of chi squared nu such that the calculated value chi squared C is less than equal to chi squared 1 minus alpha nu. If H1 sigma squared less than sigma squared naught, then the rejection region consists of all chi-square values such that the calculated value is greater than equal to chi-squared alpha nu. For the two-tailed test, the rejection region given by the low area chi-squared c is less than equal to chi-squared 1 minus alpha by 2 nu, and in the upper area chi squared c greater than equal to chi squared alpha by 2 nu. Explaining it with the help of an example as a gun-like apparatus has been designed to replace needles in administering vaccines. The apparatus can be set to inject different amounts of the vaccine, but due to random fluctuations, the actual amount injected is normally distributed with mean equal to the desired setting and with an unknown variance sigma squared. It has been decided the apparatus would be too dangerous to use if sigma exceeds 0.10. If a random sample of 20 injections result in a sample standard deviation of 0.08, should use of the apparatus be continued at 5% level? The test for standard deviation is performed as a test for variance. Given that n is equal to 20, s is equal to 0.08, alpha equal to 0.05, the null hypothesis sigma squared equal to 0.01 versus the alternative h1 that sigma squared is less than 0.01. He obtained chi-squared calculated value as 19 times 0.0064 divided by 0.01, which is equal to 12.16 with degrees of freedom nu equal to 19. Now chi-square 0.9519 is equal to 10.117, which is less than the calculated value 12.16. Therefore, we do not reject H0 at 5% level of significance. The apparatus should not be used as there does not exist strong enough evidence in favor of the alternative that sigma is less than 0.10. Each row in the table for chi-square distribution gives us right tail areas of the chi-square distribution for alpha values 0.995, 0.99, 0.975, 0.95, 0.90, 0.10, 0.05, 0.025, 0.01, and 0.005. If the calculated value of the test statistic coincides with a listed critical value, then the p-value can be directly obtained. However, this is a very unlikely situation. In all such cases, we can only obtain the lower and upper bounds of the p-value. For example, if the calculated value chi squared c 10 is equal to 16.8, then p-value lies between 0.05 and 0.10, since chi-squared 0.0510 equal to 18.307 and chi-squared 0.1010 is equal to 15.987. The null hypothesis would be rejected at alpha level greater than equal to 0.10 but not at alpha level less than equal to 0.05. Note that if we are required to test for standard deviation of the population, we have to first convert it into a test for variance, as the chi-square test is only applicable to variance. Also, the test statistic will have the chi-square distribution only if the population is normally distributed. Next, we will talk about goodness of fit test for the population. The sampling distribution of the sample statistic or estimator depends on the population distribution, sample size, and the sampling technique. We have assumed throughout that the method of simple random sampling is used in selecting sample units. The sample size is determined so as to reduce the probability of type 2 error, or even both types of error, to tolerable levels. Very often, we assume that the population has a normal distribution. It may be prudent to test if the assumption is justified. In other cases, we may believe the population has a particular form, for example, binomial or Poisson or uniform distribution, and desire to test whether we are correct in our belief. The test for population form is also known as the test for goodness of fit. The approach to this test is to first assume a particular form. This gives us a null hypothesis. We then compare the expected values of the random variable with the observed values to see how well the observed data matches the expected values. Given the total sample size, the expected or theoretical frequencies EI for different possible values of the random variable or event are calculated by making reference to the assumed distribution. The observed frequencies OI are taken from observed sample. If there is a significant difference between the observed and expected values, we can conclude that the assumption made about the population is not supported by sample data. The test statistic has a chi-square distribution, hence the test for goodness of fit is a chi-square test. The test statistic is chi-square equal to the sum of OI minus EI squared divided by EI, where there are k possible distinct values of the variable and the total frequency is n. Then EI is n times probability of xi for I equal to 1 to k, and sigma OI summed over 1 to k will be equal to sigma EI summed over 1 to k equal to n. If each of the observed frequencies exactly match the corresponding expected frequencies, chi squared equal to 0. Greater the discrepancy, greater is the value of chi squared. We can use the tabulated critical values of chi squared to test the null hypothesis at the desired alpha level of the test. The degrees of freedom nu will be determined by the number of restrictions imposed by the number of estimated parameters used in calculating the EIs. If the number of restrictions is j, then nu is equal to k minus j. Explaining it with the help of an example as three coins are tossed together a total of 120 times, and each time the number of heads turning up is observed. So the number of heads will be from 0 to 3, 0, 1, 2 and 3, and the observed frequencies are 18, 60, 32 and 10. Would you use the coins in a game of chance? Test at 5% and at 1% levels of significance. Solving the question. Now n is equal to 120, k is equal to 3, probability of a head is unknown but assumed to be half by the null hypothesis of unbiasedness. Therefore, nu is equal to 4 minus 1 equal to 3. The null hypothesis is coins are unbiased, that is a binomial distribution for n equal to 3 with p equal to 0.5. Alternative hypothesis H1 is that coins are biased, that is a binomial distribution for n equal to 3 with p not equal to 0.5. We have the table showing first row giving the outcome number 1, 2, 3 and 4. Second row number of heads 0, 1, 2 and 3. Then the third row has a probability of getting x number of heads, again for 1 upon 8, 3 upon 8, 3 upon 8 and 1 upon 8. Expected frequencies have been calculated EI and observed frequencies are obtained from the data. Then we have calculated for each one of them OI minus EI squared upon EI. The calculated value of chi squared is equal to the sum of the last row of the previous table zero point 0.6 plus 5 plus 3.75 plus 1.67, which is equal to 11.02. And u is equal to 4 minus 1 equal to 3. Now chi squared 0.053 is equal to 7.815, and the chi squared 0.013 is equal to 11.344. Firstly, since 11.02 is greater than 7.815, H naught is rejected at the 5% level of significance. The sample evidence is strongly in favor of H1 and the coins are biased. These coins should not be used in a game of chance. Secondly, since 11.02 is less than 11.344, we do not reject H0 at the alpha level 0.01 and the coins may be used. Now we will talk about goodness of fit test for independence. This category of tests is aimed at distinguishing between random variables or events which are independent and those that are not. If the test reveals that two random variables are not independent, then we can conclude that they are associated. However, the test does not tell us what is the nature of dependency. The test can be applied to random variables which can take numerical values as well as to attributes which are characterized by mutually exclusive categories. For this test, we need to first arrange the sample data in a two-way classification table or a contingency table. Let the two random variables A and B. If A has H categories and B has K categories, then there will be a H by K matrix of all possible combinations of A and B categories. The observed frequency for each combination of A, I and Bj, where I can take any value 1 to H and J can take any value 1 to K, denoted by Oij, is written in the corresponding cell of the table. The row totals give marginal frequencies Ri of Ai. Similarly, the column totals Cj are the marginal frequencies of Bj. The total marginal frequencies of A will equal the total of marginal frequencies of B. This total is a sample size n. The contingency table illustrates that if A and B are independent, then by multiplication rule of probability for each pair AI and BJ, probability AI intersection BJ is equal to the product P of AI times P of BJ. And the expected frequency is Eij is equal to n times P of AI times P of Bj. Although P of AI and probability of Bj are unknown, they can be estimated as P hat of AI equal to Ri upon n and P hat of Bj is equal to Cj upon n. The estimated expected frequency is Eij equal to Ri Cj upon n. If the two variables are independent, the expected frequencies should be quite close to the observed frequencies Oi and j. The expected frequencies are calculated under the presumption that A and B are independent. The test statistic for independence summed over I and summed over j, Oij minus Eij square upon Eij, has approximately a chi-square distribution. If the observed frequencies are fairly in agreement with the corresponding expected frequencies, then chi-squared will be small. If there are large deviations between observed and expected frequencies, chi-squared will be large and we can conclude that the two variables are not independent. The degrees of freedom associated with the contingency table is r minus 1 times c minus 1, where r is the number of rows and c is the number of columns, since there are only r minus 1 independent rows and c minus 1 independent columns. Explaining it through an example, the following table is obtained in a study of a company's job training program. Examine whether on-the-job performance of persons having undergone training is independent of their IQs at the 5% level of significance. It can be solved as follows. The null hypothesis is that performance is independent of IQ, and the alternative hypothesis is that performance is not independent of IQ. Now, in the table, we have got the cells giving combinations of performance and IQ. And the column totals for performance 63 for average, 27 for good. Similarly, the row totals 40 for average IQ and 50 for good IQ. And the total of the rows as well as of the column totals all add up to 90. That is a sample size. Now we calculate the expected frequencies E11, E12, E21, and E22. After that, we are able to calculate chi squared so that we have 30 minus 28 squared upon 28 plus 10 minus 12 squared upon 12 plus 33 minus 35 squared upon 35 plus 17 minus 15 squared upon 15, which adds up to 0.1429 plus 0.3333 plus 0.1143 plus 0.2667 equals to 0.857. Degrees of freedom is equal to 1. Since we need to have only one of the cell frequencies once the totals are known to be able to fill in the remaining cells. Now chi squared 0.051 is equal to 3.843, which is greater than 0.857. Therefore, we do not reject H0 and conclude that performance of persons having undergone training is independent of IQ. Thus, to summarize, unknown population parameters are estimated with the help of sample data by using the appropriate estimator. The same estimator is also required in tests of hypotheses, where sample data is used to test the claim represented by the null hypothesis. In both types of inferences, knowledge about the sampling distribution of the estimator or sample statistic is required. Secondly, the parameter to be estimated, type of population distribution and sample size determine which test statistic based on the sample statistic is to be used. The same holds true for problems involving tests of hypotheses. Thirdly, in deriving confidence intervals of unknown parameters, we have to first specify the level of confidence and consider the sampling distribution of the estimator to arrive at the confidence limits. Fourthly, in hypothesis testing, we initially assume the claimed value of the parameter is true until the sample data strongly favors the alternative and we reject the initial or claimed value. Next, the rejection region in tests of hypothesis and the confidence interval are disjoint sets where the level of confidence and the significance level of the test sum to 1. An alternative method to the rejection region method is the p-value method. In addition to testing for a particular parameter value, we can also test whether our assumption about the form of the population being sampled is justified. Goodness of fit tests can be used to infer about the independence or the association between two random variables. The estimates or tests illustrated in this module involve the Z, T, chi-square and binomial distributions.